Hi guys, this is Arias, your physics instructor. Today we will be solving a question from Unit 4, which is very common, and also a question that is also mistaken at a lot of times is the vector diagram, which can be used to derive the equation A is equals to V squared over R, where A is the centripetal acceleration, V squared is the centripetal linear velocity, and R is the radius. So let's see how it's actually derived. Okay. Let's have a look at the question. All right. An object travels with speed v around a circular path of radius r. The diagram shows two positions va and b on the path. The acceleration of the object is a. Derive the expression a is equals to v squared by r. So um now we have to keep in mind over here where the both of the vectors are actually going, because they actually told us to include a vector diagram. So over here, we could see that VA, we'll consider this as VA. Okay. This is VA. And this is VB. I'm so sorry. It's not proportional, but it's somewhat around that. And over here, we have the angle theta. So this is going to be our main turning point. So let's draw the vector diagram. So we already know that both of the VA and VB are going like this. So this is VA, okay? And for vector diagrams in this case, they have to start from a single point. So let's take VB like this, okay? So that's VB. Now over here, we do know that they're separated by an angle theta. So we will take the angle theta over here, okay? This is a very small diagram that I've just drawn. And over here, this is the main thing that you have to do. This that we have to connect both these, and it's going down like this. This is our change in velocity. Okay, very important that we note it down. Now, from this, using Pythagoras' theorem, you will come across an equation that will be sine theta is equals to change in velocity divided by VA. So basically, we are taking around this one and this one. Okay. And one thing that you have to remember, and the reason why we didn't take VB, is that this is an isosceles triangle. This is isosceles. So for an isosceles triangle, we do know that VA will be equal to VB. Okay. So that is why we could either take VA or VB, no matter what. Just the change in velocity is different. Now, how do we deal with the sine theta? This is a very confusing part, all right? Over here, we do know that this theta will be very small, all right? It's very small. So no matter what happens, the sine symbol, it actually disappears. So because of that, we have to write small angle. Okay? This is actually where your mark lies. Just this small thing. This is where actually your mark will lie. All right? Okay, now from this, we have to get our derivation of A is equals to V squared by R. So we do know that our W, or in Greek, it's a this is basically the centripetal velocity. Okay, This is the centripetal speed, which is, we know that it is the change in angular displacement divided by time. All right. I'm so sorry. This is the angular velocity. My bad. Okay. This is the angular velocity. Just give it down. All right. So we have the angular velocity over here, which is change in displacement, okay, divided by time. Now, we also know that the linear speed, all right, we could denote it as VA or VB, no worries, is actually the radius times the angular velocity. All right. From here, we could denote that the angular velocity is equals to VA over R. All right. Pretty simple. Now we have two equations for the angular velocity, one right here and the other one right here. We take this into account. All right. So we could take VA over R is equals to change in angular displacement divided by the time. We already know that since sine theta over from this vector diagram that we got is very small, so we will just denote it as theta is equals to change in velocity divided by VA. Okay, this is actually change in angular displacement that we will be calculating here because this eventually increases. Okay, now if we take from this point of view, all right, change in angular displacement. So we could actually bring this over here. Okay, you could just directly bring this over here. Now, once we bring this, we actually will have VA over R is equals to change in velocity divided by VA over time, right? So, if we were to bring this VA over here, you would come up to an equation something like this: change in velocity, VA times T. All right. From this, let's multiply this with this and this with this. Okay. So in this case, it would be, since we have VA over here, okay, so we will have VA squared times times T. Okay. VA squared times T, we will have change in velocity times R, right? Okay. Now this is where we have the turning point. I'll do this in a different color so that we show the proof. Okay. This proof we could denote it as VA squared. All right. What we're doing here now is that we are bringing the R over here and we're bringing the T over here. Now, once we bring the R over here, this will be equals to the change in velocity divided by time. I hope that we've learned in IGCSE and almost in every form of physics that we do know that this is just an extra note that I'm showing just in case is A is equals to V minus U by T. This is the change in velocity. Okay. Divided by time. We basically have the same thing over here. Yeah, that is our acceleration. And that is why we can denote this as V square because VA and VB are similar due to an isosceles triangle A. And therefore, A is equals to V square by R. So this was a this is somewhat a bit of complex problem. I hope that this video helped. And for more physics, please do sign up for our Elevare classes. We will be having um, past paper problems like this. We will be solving them. We'll be going throughout the syllabus, and we're just gonna make physics a really, really important part of our lives. So thank you very much for watching. Thank you.